Good afternoon, everyone. My name is William Beordo, and I'm first-year PhD student at the University of Turin and at the Astrophysical Observatory of Turin. In this talk, I would like to show you something about my PhD research in the field of gravitational astrometry and fundamental physics to test the dynamical evolution of our galaxy and its place in cosmology. So, as anticipated by Sonia, with the advent of Gaia, we can undoubtedly speak of gravitational astrometry. That's because Gaia is providing an accuracy of few microseconds, and with such a high level of accuracy, we are forced to consider the local geometrical environment affecting the light propagation from stars to our Gaia telescope. For this reason, the Gaia processing, data processing, makes use of a fully relativistic inverse ray tracing methodology. Therefore, given the fact that Gaia data are fully general relativistic, we need a general relativistic model also for the Milky Way, as well as properly defined kinematics in the general relativistic framework. This would allow us to have a local cosmology laboratory in which, against which any model of the galaxy can be tested. A first test for our general relativistic picture of our galaxy is clearly the rotation curve. To date, the general assumption is that on galaxy scales, the gravitational field and the general relativistic effects are usually small, so one can use simply the Newtonian limit. But however, with these ansatz, a massive dark matter halo is required in order to explain the effect profile of the rotation curve. But now, with the general relativistic data provided by Gaia and with the observational challenges that dark matter paradigms have to deal with, we are forced to wonder and prove if the Whitfield limit of general relativity coincides with the Newtonian regime. In fact, it turns out that non-diagonal contribution of a galaxy post-Newtonian metric is of the order of 100 microseconds, which is already within the individual error of Gaia. Cross-time collaborators try to answer this question for the first time using a general relativistic model for our galaxy and using Gaia data release 2. The answer would appear to be negative, since the flat rotation profile can be reproduced in a way that is statistically equivalent to that expected most recent models with dark matter. But here, the role is played by the background geometry of the space-time without need of extra mass. So we want to build a general relativistic picture of our galaxy, and this could be the starting point to pursue this aim. So here, the underlying general relativistic model comes from the work of Balazs and Green-Miller and starts from a stationary and axisymmetric space-time with a reflection symmetry with respect to the galactic plane, where the stress energy tension is the one given by a pressureless perfect fluid. So basically, we are thinking of a galactic disk that is made of stars that can be seen as dust grains with no interactions or pressure. In this way, we can consider the rotation curve only due to the angular momentum sustained stellar population. Then, by solving the corresponding Einstein equation, Balazs and Green-Miller proposed a 3-parameter model for the metric function n. with R0 is the size of the bulge, big R the size of the disk, and V0 the velocity in the flat regime. Moreover, from this other equation, we have a further metric function nu that can be constrained only through the relativistic density. However, this model is no more valid near the rotation axis and for z greater than r0, because here the velocity exceeds the speed of light. Once we have set a general relativistic model for our galaxy, we need to define a suitable observer. In such a space-time with stationarity and axis symmetry, a generic observer has these for velocity, and where beta is the angular velocity with respect to angular momentum with respect to the infinity. And a particular class of observers are ZAMOs, which are locally non-rotating frames, and with zero angular momentum with respect to infinity. The velocity measured by such an observer can be written in this way, and it comes down to the expressions for a static observer like Gaia. And this represents the velocity of the co-rotating star as measured by an asymptotic observer, which is at rest with respect to rotation axis. And as we see, it is proportional to n, which is the metric function, and also the off-diagonal term G0 phi. So this is a pure general relativistic effect that we call gravitational dragging. Now we would like to select a sample of stars that can trace the rotation curve on the galactic plane. Therefore, starting from the early data release 3, we looked at sources cross-matched with 2MASS, as for the DR2, but adding young giants. Then we applied the usual selection for the availability of the 5 astrometric parameters plus the radial velocity, and then also a kinematic selection to retain only thin disk stars, basically those that are in this small region of the Tomori diagram. And are stars with low velocity dispersion and with nearly circular orbits. And finally, we selected only stars close to the galactic plane. This gives us a sample of more than 800,000 stars, which is enormously larger than the previous one from DR2. And with the upcoming DR3, we plan to apply a more meticulous astrophysical selection to retain only OBA stars. And here, and what we find, also for the DR3, thanks to which we gain about 3 kiloparsecs toward the galactic center, is that basically both the relativistic model, the BG model, and the classical model with Armada are statistically equivalent. And the interesting thing is that we find very reasonable parameters for example, for the size of the bulge and for the size of the galactic disk. Moreover, also the radial profile of the relativistic density shows a behavior that is similar to the one of the baryonic only contribution of the classical model with Armada, but requiring even less mass. Unfortunately, we have only one reliable estimate for the baryonic density, and therefore we are forced to constrain the metric function nu only at the sun position. But however, if more measurements of the baryonic density were available, we could determine a more general function for the metric function nu, and thus verify the overall consistency of the BG model. To directly quantify the gravitational dragging contribution to the relativistic rotation curve, we calculated the effective Newtonian rotation curve that is produced by the relativistic mass density by solving the Poisson equation. Clearly, this effective velocity should be equal to the baryonic-only contribution of the classical model, but however, due to the critical regions of the BG model near the rotation axis and for z greater than r0, we have to minimize the difference between the two curves over the disk thickness used to compute the effective velocity. So
sorry,
yeah, okay. So the gravitational dragging contribution is therefore given by the difference between the relativistic rotation curve and the effective Newtonian rotation curve, and we clearly see that the gravitational dragging mimics the Darmada contribution pretty well, and this without need of extra mass, but only thanks to the background geometry of the space-time. So these results confirm also with the early data release 3 seems to be very promising. So what we can do next? Well, since the BG model can be only applied near the galactic plane, we would like to go beyond it. For example, starting from a more general space-time, where additional conformal factors could be constrained with Gaia data, could be useful in order to include and describe all the different Milky Way structures and find more physically robust solutions with matching boundary conditions between these structures. So our challenging aim is to build a general relativistic a framework for our galaxy that is as more general relativistic as possible. In this regard, the Milky Way can play a reference role for external disk galaxies. But on the other hand, external disk galaxies with properly defined kinematics could give us more hints about for example, the baryonic density from measured Surfer-Brannus profiles, and also about the effect of the gravitational dragging, as it's supposed to sustain their flat rotation curves, as like for this galaxy. So given these results, we we believe that it's worth going in this direction for future work. Thank you.
Thank you. Thank you very much. Good timing also. Yeah. Is there any question? Yes, please.
I don't know what to say. You have left me speechless.
Okay.
I'm not an expert in general relativity, but you're telling me that with the general relativity, you can explain flat rotation curves without using bond or dark matter. That's outstanding. I don't know why I haven't heard about this before. But something that makes me skeptical about this is that all kinds of these galaxies have flat rotation curves, little galaxies, large galaxies. And in all cases, you think that this effect you're talking about will explain a universal flat rotation curve despite all the variations in the visible part of this galaxy?
Yes, this is what we would like to prove, that the Milky Way can serve as a reference role for all external these galaxies. So from we could, for example, have different parameters for the model, but the same simple flat rotation curve.
So because that's a big challenge.
Yeah.
To start with all the different these galaxies that you can see.
It is very challenging.
A flat rotation curve in all the cases.
Yeah.
I may had a comment that, of course, there was an attempt, it was an ansatz, let me say, in physics ansatz were known. So the beginning to try to, with the Gaia data, to fit this relativistic model, that model, and apparently it works. And this parameter and are fitted also with external galaxies. So are very quite predictive this profile. Of course, we had to add more data that are general. The main problem issue is that we don't know to solve Einstein equation because they're very complex to solve Einstein equation. But the advantage of this approach that with the Einstein equation, we have basically one equation for the density, another equation for velocity profile. So they are independent equations. They are, of course, linked by the Einstein equation. So from one side, you have fitted the baryonic density without need extra matter. On the other side, you fit the profile velocity without link univocally to the Boltzmann equation. This is the main problem with classical model. Is the link velocity with Boltzmann equation. It's not enough. The challenge with we are going to first is to what extent our galaxy is general relativity. To what extent weak field in general relativity is giving new insight with respect to cosmology. We will see with the next Gaia data and the William will work.
You're choosing dark matter, and Sonia was talking about Darkino.
No, be careful. Darkino is the photon, it's light, it's not dark matter. So this is the first talk of William, and I would like to
Yes.
the very first talk.
As I said, I'm speechless.
Yes.
Is there any other question? No, online either? No? Well, we are all speechless, so let's thank our speaker again.
Thank you.
And yes, good luck with
Thank you.
your three. Huh?
Thank you very much.